start in on the GC mass spec so we can get more information on those techniques that take more information. Your homework will be posted today. One of the things I'm going to do on that is another NMR problem where you're going to do the same type of structural proof that I did on Friday, and I'll do a few more of those today just to give you practice using that technique to do spectral determination. And then some more UV-Vis questions. So first off, we're going to start with the NMR stuff, but if you're keeping track, reading the first part of chapter 7, 7.1 to 7.6 for day, and then for tonight, 7.7 to 7.13 for Wednesday. Hold that for a second. The writing awards. I mentioned this earlier, but the writing award for juniors that are taking classes and will be here next year, those are due on Friday. So if you have something you want to submit for the writing award, be considered as $500 scholarship if you are selected as the winner. So those are due on Friday to the main office, and there's instructions on how to do that outside of the main office. Today, and the first one here is an interesting structure. So the structure that this spectrum corresponds to is this dimethyl acrylamide, where there are two methyl groups on the nitrogen of the amide. Normally, if we were just looking at the structure, we would say those two methyl groups are equivalent because they are connected to the same nitrogen, and for like an isopropyl group, we would say these two methyl groups are equivalent. But as you look at the spectrum, you're going to notice that there are actually two singlets right around 3 parts per million. These two singlets are actually the two different methyl groups on the amide group. On an amide in particular, we have a very strong resonance form, which we've seen in the IR when we were talking about amides, where the nitrogen takes on a positive charge and the oxygen a negative charge. And we get a double bond between the nitrogen and the carbon. Remember, double bonds cannot rotate. Turns out that this resonance form is so stable, or contributes so much to the overall structure of an amide, that it has partial double bond character in the whole structure. So if we drew out the resonance hybrid, this partial double bond character makes it so that the amide double bond, or the amide nitrogen carbon bond, does not rotate easily at room temperature. You've got to get it more energy in order to get that bond to rotate. I mentioned earlier that NMR is kind of a slow process to take an NMR. So most of our methyl groups, if they're on an isopropyl group, are going to average up because there's rotation around the single bond, and you can average those out. There are some structures, though, that don't rotate fast enough on an NMR timescale that you can actually differentiate them. Amides are the primary one that this happens in. So when you have an amide group, you're going to have two signals. If we were to heat this sample up and give it more energy, you actually see those two signals coalesce into a single signal. So if we were to run this at, say, 100 degrees in the NMR, we would see just one signal because we'd give it enough energy that it would be rotating around that bond. This is only for amides. It does not work, or we don't see this, if we were to say have an amine. If we took away the carbonyl group and we just had this allyl dimethylamine, we would see these two groups as equivalent. And we would have just one structure, or one peak in the NMR. So that's a special case with the amide. We're going to go through another peak for structure determination here. So we have the peak. We want to have the chemical shift, the integration, splitting, and conclusion. So I have 5 peaks here. You can start on either end. I'm going to start on the end that's closest to me. So this is about 6.6 parts per million. The integration for this one, if I measure from here to here, if I take that, those are about equivalent, and then these ones are about 3 times higher. So we're going to assign 1 to that integration. If you're doing this on your own, you'll want to measure the difference in that height, and then divide by the smallest one to get your ratio. But I know from the structure that that corresponds to 1. And this splitting pattern, although we haven't talked about it, is a doublet of doublets. So it's a doublet here that's been split into another doublet. And that's why, even though there's 4 peaks, it's not the standard quartet structure that we would see in a, if it had 3 neighbors with the n+1 rule. Then we have a peak at 6.3, also an integration of 1. It is a doublet. Peak at 5.7, integration of 1, it's a doublet. And then we have the 2 peaks, one at 3.1 and one at 3.0, each of them corresponding to 3 hydrogens, and each of them a singlet. The conclusion we can draw, if we look at the range of these first 3 peaks between 5 and 7, is our alkene regions. Those are the type of numbers that you should know for the test. So the table in your book, there's a table in your book with kind of the common chemical shift values. You should know those for the test.
And how do we know that those 2 singlets aren't just one doublet, since they're so close to each other?
We wouldn't know for sure. Yeah, that is a possibility. The thing you would have to know is that somewhere else, if that's integrating to 6, there needs to be something that is split into a 6+1 septet. And we don't see a septet in the structure. Yeah, that's a good question though. You don't want to make assumptions. So all of these are in the alkene region. And there are 3 of them. So if you look at a standard alkene, there are 2 carbons with spots, or 4 total things to be attached to the alkene. In this case, we have 2 hydrogens on 1 carbon and another one. Now, another assumption you would not want to draw is just because there's 3 in this region doesn't mean there's just 1 double bond. It could be that there's 2 different double bonds, one with 2 hydrogens and one with 1. You would have to know from the molecular formula whether that's a possibility or not. In this case, we know the structure, and so we know that there are only 6 total hydrogens and 6 carbons, so it's unlikely that it's 2 different alkenes, especially since we know we have those methyl groups over there. So we know there's 3 hydrogens in just 1 thing attached to the alkene. The splitting, if you look at this, the alkene, you can't rotate around a double bond. And so each of these three peaks is going to be different on an alkene. Unless you have some type of symmetry around the alkene, that's always going to be the case, that you're going to see a different peak for all the different hydrogens attached to the alkene. And it has the more complex splitting that we'll talk about later. Actually, if you look at this even closer, there is very, very fine splitting, probably from a longer distance coupling. Then we have the two methyl groups, so we know that they have a ppm of about 3, so it's attached to some type of heteroatom that's deshielding, and we have a methyl group. And then you would want to try and piece that all together to give you the final structure. You'd probably need a little bit more information to know that it was enamid with a carbonyl attached there. So you'd probably need either an IR and carbon-13 NMR to really know that, unless I gave you a hint.
Which hydrogen is the double?
I was going to go into that, and then I was debating with myself whether I should. Because it probably will assign it wrong. I'm trying to remember what the coupling constants are. It turns out that the 2-carbon coupling constant, these two, these can couple each other. And then I'm pretty sure that this is actually one of these two. And then they're coupling each other and coupling this one. And I don't know which one it is, because the cis coupling constant's different than the trans coupling constant. I can't remember which one's higher. I think the trans is higher, but I can't remember exactly the numbers.
With the methyl groups of the nitrogen, you have to assign which one is which peak? Is there anybody know which one's up or down?
No, you don't need to assign which one is which. Okay, a couple other examples, things to look for. So this one also has peaks in the alkene region, 5 to 6. We have 3 of them, and so they're each 1 hydrogen. And in this one, we get even more complex splitting. But we also have a peak at 3.9 that is split into a doublet. So we have a doublet here. Note that these peaks are closer together than these two, so they have different coupling constants, so we know they're not splitting each other. And they have an even different coupling constant than that one. So we know that all 3 of these doublets are not splitting each other. They all happen to be splitting the one at 6, and that's why we get the craziness of that peak. This corresponds to C3H5Br. So if we were to calculate the units of unsaturation, we've got 2 times 3 plus 2 minus 1 for the Br. So it would be 6, 7. And we subtract off the 5, we get 2 hydrogens that are missing, so our units of unsaturation is 1. So we have 1 unit of unsaturation, which we should be able to identify as an alkene because it is in the 5 to 6 region there for the alkene peaks. Again, we have 3 hydrogens in that region, so we're going to have the 3 hydrogens off of the alkene. And we have a Br group. So we know the Br group is not attached to the alkene because we need 1 more carbon here through the C3, 1, 2, 3, and that's going to be here. So in this case, this hydrogen has 3 different sets of peaks that are splitting it, giving it a rather complex, let's see, that's a doublet, triplets there. Because it's split into a doublet by that, split by that for a doublet, and then there's 3 hydrogens there. Yeah. questions on that one? Anything else I want to say about that? That's about it. We already talked about alkenes. The chemical shift of the peak around 4 indicates that it's attached to something very electron withdrawing, and if it's alpha to a alkene, that will shift it up a little bit. Remember that alpha to an alkene would be the next carbon over from a functional group, so alkenes and aromatic rings and carbonyls are going to shift the peaks a little bit downfield to higher ppm.
Multiplet, like if we were gonna, or if we were gonna make one of these part things for that, would we have to like integration and like, so would that be like 1.5-ish?
Do the integration should correspond to, let's see, yeah, they're about all 1 to 1 to 1, the integration. For something like this, you can say multiplet at this point. The last example I wanted to talk about has the aromatic region in particular. The aromatic region, again, if you have an aromatic ring, you know that you have the standard benzene core, so you have the 6 carbons, and in a standard benzene you'd have 6 hydrogens. But then you want to look and see how many peaks you actually have in that aromatic region, and look to see what type of substitution pattern you get from the signals in the aromatic region. In this case, between 7.5 and 8, we have 1, 2, 3, 4 peaks in that aromatic region. And we'll make up a little table the same as we have. The molecular formula for this is C6H5ClO. We have our peak, we have our chemical shift in ppm. Just as a tip, if you're making a table that all of the things in that column have the same units, it's always helpful to put that in the title of the column so that you don't have to keep writing ppm over and over and over again. So we have 4 peaks in here. 1, 2, 3, 4, 5, and 4 peaks. No, 5 peaks. Yeah. That's why I wrote 5. I'm just going a little crazy. 10.6 ppms per first chemical shift, and we compare the integration here. It's about 1, 1, 1. They're all the same integration, so they're all going to be 1 in this one. And the splitting, this is going to be a broad singlet. Then we have peak at 7.9. 1 hydrogen. This one is a doublet. Technically a doublet. Doublets with really fine splitting, but we're going to ignore that. 7.6. We have 1 hydrogen. This one is a triplet. 7.1, 1 hydrogen. This one is a doublet. And 6.9, 1 hydrogen. That one is a triplet. So a broad singlet indicates what? carboxylic acid or an alcohol, something that can hydrogen bond, which gives it the broader signal. Another clue would be if I said that I added D2O, what's going to happen?
It goes away.
Goes away. So yeah, that peak does go away. Looking at our molecular formula, what do you think it could be? We have a chlorine there, but that wouldn't have the OH on it. Alcohol. So in this case, we know it's an aromatic ring, right? So we need 6 carbons to make the aromatic ring. And that leaves us with no more carbons to make a carboxylic acid. We also don't have 2 oxygens, so we can't make an acid, carboxylic acid. And so in this case, it's just a phenol. Also, the chemical shift is high for an alcohol, so it's a phenol rather than a alcohol, often say a CH3 or a CH2 group. You know, yeah, it's a phenol. Then we have the 4 peaks in our aromatic region. They are going to tell us what type of substitution pattern we have on the aromatic ring. If you have 4 things attached to an aromatic ring, or sorry, if you have 2 things attached to an aromatic ring, there are 3 different substitution patterns you can have. The ortho, the meta, and the para. And these will give you distinctive splitting patterns in the NMR so that you can identify what type of structure it is. The one caveat being that these are, if it's unsymmetrical. If it's symmetrical, you're going to get a different set. So this one, if it's unsymmetrical, you still get the 2 hydrogens that are the same because it's going to be symmetrical through here regardless of what's attached to the 2 ends. And so we're going to get 2 signals, and they are going to have 2 hydrogens and be split into doublets. That's very distinctive of a para-substituted aromatic ring. Meta-substituted does not have any symmetry, and so you're going to get 4 signals. This signal here will be 1 hydrogen, and it's a singlet because it doesn't have any neighbors 3 bonds away. The 2 next to them will be 1 hydrogen each, and they are going to be split into a doublet because they have 1 neighbor. This one is also going to be 1 hydrogen and a doublet. And then our last one is going to be 1 hydrogen and a triplet because it has 2 hydrogens that are neighboring it. The ortho also has 4 signals. In this case, the 2 that are right next to the substituents are going to be 1 hydrogen and a doublet because they have 1 hydrogen neighbor. This one's going to be 1 hydrogen and a triplet, and this one's going to be 1 hydrogen and a triplet as well. So now, going back to our structure that we have here, we have 4 signals. So we know it's either ortho or meta, and they each integrate to 1, and we've got doublet, triplet, triplet. So that tells us that we have a ortho substituted structure. In this case, the only other things we have to attach are the OH group, which we identified already, and then the chlorine. So it's an orthochlorophenol for the final structure. Sheldon?
Is it possible for the order of those to be different, like double, triplet, or
Yeah. So you note if you were to go around the ring, it it's doublet, triplet, triplet, doublet, and they can show up in any order. You just want all four of them. If you want 2 doublets and 2 triplets within the 4 signals. Otherwise, we would see a singlet, a doublet, and a triplet. The challenge here, when I'm trying to find examples at least, is that you want to have the right electronegativity balance so that it spreads out all the signals. The first example that we looked at here, this had 3 signals, so we knew that they were that it was a tri-substituted benzene, but 2 of the signals were overlapping each other. And that can be pretty common in the aromatic region because it's a kind of small region, so you get peaks that are overlapping and you want to kind of look as closely as you can to identify whether that's 1 signal or 2. In this case, we could tell because one side was way higher than the other of that doublet. And it integrated into 2. So check your integrations and look to see if it actually looks like a splitting pattern should. Sometimes you just have to call those multiplets. So, if you have the right balance of electronegativity, they do spread out nicely like this, but they don't always do that.
I had a question. The peak at 6.9, which you call a triplet, that doesn't really look like a typical triplet where you expect them to be 3 times, right? So how would you differentiate?
The problem with this one is that, where did you yeah, the line of the graph.
It's really dark.
I can zoom in really close. The line of the graph is, of course, just right at the same area of as our peak, and so you can see where it stops going up and being dark is right about there, which is pretty. I wonder what the other ones. What's the other challenge? It's not hard enough. Other questions?
I see on your notes that you labeled this as a nitrous balance and like
Oh, what's wow.
so
Someone
other
wrote
than
down the notes.
being like given the
You'd have to be
formula.
given the formula there too. That's weird, there's an F right here. Yeah, you'd have to know that had a chlorine or a nitrogen in there. You wouldn't be able to identify that
Okay.
just from a proton. That's interesting.
What's that little dude right there?
So this one right here.
yeah.
So this spectrum they actually took as a mixture of DMSO and chloroform D. So they had 2 deuterated solvents in it. And when they had the 2 deuterated solvents, it actually changes the parts per million shift of the chloroform peak. Yeah. Oh, I have that saved there. So that's actually our chloroform peak. Usually it shows up at 7.26, but it's a little shifted because it's a weird solvent system and the DMSO shifts it a little bit. Any other questions? Oh, that's what we're going to cover for NMR for now. We'll come back to NMR later. Now we're going to move on to NETs. So, how many people took inorganic chemistry? Like MO diagrams, right? We're not going into too much depth.
Those were bad.
This one's getting
Big
pretty
ones.
simple.
We didn't have to do them anymore.
Those were bad.
Everything you know is a lie.
Which I think I might be doing also, except on the computer.
You have to look at one. It's a really simple one.
True, I think
I'll
it's
debate
really-
that.
It's I think it's gonna be simple.
So we're going to look at a subset of ethene here. between the two carbons. And then it's also going to form a pi bond between the two carbons. It's relevant. Just trust me.
No, it's not.
So we form the pi bond between the two p orbitals. And in your ethene molecule, we have two electrons that are going to come together in our sigma bond, and two electrons that come together in the pi bond. Now, the reason why this is relevant is that we are going to look at excitations of electrons when we're talking about UV-Vis spectroscopy. And I wanted to give you a better idea of what we're looking at here. We're looking at the excitation of an electron from the HOMO orbital, which is the highest occupied molecular orbital. So remember that that is going to be the one that is the highest in energy with electrons in it. So highest occupied molecular orbital when you draw out your molecular diagram. The next highest orbital is called the LUMO. Which is your lowest unoccupied molecular orbital, or LUMO. So we have the lowest molecular orbital that does not have electrons in it. And typically for UV-Vis, this is going to be your most standard excitation that we're going to see, is the excitation of a electron from the HOMO, highest occupied molecular orbital, to the LUMO, lowest unoccupied molecular orbital. And that is the only time I'm going to draw out the molecular orbital during this description. The rest of the time we're just going to be drawing lines and labeling them as one of them. But I want you guys to remember that this correlates to something about the molecule itself. It's not just random energy levels that we're drawing in, which is mostly what you'll see in the textbook and anywhere else you look for UV-Vis. But you should know why that correlates to the actual molecule you're looking at.
The PN cells. That's what I'm creating with, right?
So there are certain selection rules that mean that there are only certain transitions that will actually occur or are allowed according to quantum mechanics. But know that even forbidden ones can sometimes occur, just like they did in IR, because, well, we don't like to follow rules, do we? But in general, your forbidden ones are going to be lower in energy, lower in total, sorry, let me say this properly. So your forbidden ones are going to have lower intensity of absorption. So your overall absorption peak is going to be smaller if it's a forbidden one. I was going to go into some of the selection rules. I'm just going to give you one. So for selection rules here, no change in spin orientation of the electron. Remember, we're talking about electron nucleus or the neutron or proton that was in the nucleus. So when that electron gets excited, it doesn't change spin states, basically what that rule says. There are a few forbidden ones, but we're going to see them anyways. The most common one being the N to pi star, and I'm going to explain what that terminology means on the next slide. But those have weak absorbance. This is more what we're going to represent those electronic energy levels as. And we have a sigma bond, we have pi bonds. The N stands for non-bonding electrons. So you have a nitrogen or oxygen that has electrons that aren't participating in a bond. Those are going to be considered N. And as I review, the star next to the pi or the sigma stands for anti-bonding. So our pi bond here has equal energy or higher energy pi anti-bonding orbital. And there's also a sigma antibonding. So you can actually see excitation of electrons for different molecules from several combinations of these. The lowest energy one is actually the N to pi star. And if it has a lower energy, do transition, and then we'll say an approximate lambda max. So for this one, approximately 300 nanometers. Remember when we were talking about photons of light, the lower energy ones are going to be the longer wavelengths because they're a little bit lazier. So our energy for the higher numbers is going to be lower than the energy for the lower numbers when we're talking about lambda max. So this would be the excitation from N here to pi star. So that first, and you can see those are the closest together in energy out of all of them. Of course, they're all equally spaced, but that's the one that is typically closest in energy. The next one up is going to be our N to sigma star. And common values that I was finding for this would be 180 to 200. And that's going to be your N to sigma star here. Next one up, our pi star. So an excitation of an electron from a pi orbital to the pi antibonding orbital. And this has somewhere in the range of 190 nanometers for its lambda max. And that would be the pi to pi star. And you can see relatively that's going to be similar in energy from the N to sigma star and the pi to pi star. Now, potentially you could see a sigma to pi star, but these are very uncommon. And probably you're not going to see very many of those, but that would be higher in energy. And then the highest in energy one would be our sigma to sigma star. it's gonna be sigma all the way up to sigma star, and you can see that's gonna take the most amount of energy, so it's going to be our shortest lambda max, which is about 150 nanometers. And as we'll see later on, that's in a region that we really can't quantify very well, because everything that we're going to try to dissolve our sample in is going to have sigma bonds, right? Pretty much every molecule you have has sigma bonds. So if you're getting excitation from a sigma to a sigma star, we're going to be exciting basically anything you could put in the UV vis, and that's going to max out the sample absorbance. So you're not going to be able to breathe those, and all our solvents and things like that come in that region. So the ones we're going to focus on are going to be our pi to pi star, n to sigma star, and the n to pi star. Those are the most common ones we'll see. Questions on that? Now for some definitions. Oh, we'll come back to that. It's great. So, definitions. Groups of a chromophore is a group of atoms responsible for an electronic absorption. So we have what we call functional groups in organic chemistry. Chromophores tend to be like functional groups, but you're not limited to just, say, if you have a ketone, it's not necessarily just the carbon and the oxygen. If we have a conjugated ketone, you're going to have other double bonds that are going to correlate with that. And so they're going to be part of the chromophore. So it's generally our functional groups, but maybe an extended group. One common example would be a really long chain of double bonds that are alternating double bond, single bond, so they're all conjugated. That's going to be kind of one chromophore. We just see one excitation in that one. Oxochrome is going to be a group of atoms which, when attached to a chromophore, alters the wavelength and intensity of absorption. So a couple examples would be, say, an alcohol or an ether, an amine, a halogen, or even a methyl group. All of these would be considered oxochromes. So if we were to represent this graphically, the cartoon, you've got your core chromophore, your oxochrome is just going to be something that's directly attached to it. Like so. And those need to be only one bond away. some more definitions. Bathychromic shift is a red shift. And that's going to shift it to lower energy or longer wavelengths. So then the hypsochromic shift is going to be a blue shift. We're going to go in the opposite direction to higher energy or shorter wavelengths. Hyperchromic shift is a shift where it increases the absorbance or the absorption intensity.
Is there no color?
Nope. And I'll show you why in a second. And a hypochromic shift is a decrease in absorption intensity. So, this can be represented graphically. Again. So if this was our UV vis spectrum, here's our absorbance, here's our lambda, or our wavelength, and let's say this is our typical UV vis spectrum. Increase in intensity is just going to give us higher absorbance, so that would be a hyperchromic shift. And decrease in intensity is going to be a hypochromic shift. It's just the amount of absorbance that you're seeing is changing. The bathochromic shift and the hypsochromic shift are going to change where on the x-axis we are. So if we're going in a red shift, we're going to be going higher wave numbers. For a bathochromic shift and a hypsochromic shift, would be to shorter wavelengths, higher energy. Maybe a little bit easier to remember graphically. Any questions on that? So we're talking about one transition from, say, pi to pi star in your system, and you would think that that would just take one energy light. So one photon of light at the exact energy is going to give us that absorption. But it turns out that your peaks are actually a combination of electronic transitions to the different electronic energy levels, but we've also got vibrational energy levels and rotational energy levels that are interspersed within those electronic energy levels. So here, the black line here at the bottom is our electronic energy, and here is the next energy up. But we can get absorption from the lowest energy, vibrational, and rotational energy to the lowest energy, but you could also go from there to the next rotational energy with a little bit more energy, and to different rotational energies, so say we're starting here, going up, or starting here, going up. And all of those are going to show up on the spectrum here. And so the one where you're the lowest vibrational and rotational energy state is going to be the lambda max. But then you have all the electronic states, or the rotational states and the vibrational states. And this is why our spectrum ends up being a very broad peak, like this, because it's actually a compilation of all of those different energy levels, and we don't see all of those, we just see the broad peak, we don't see the fine definition between all of that. In this case, there's actually 2 peaks. We'll be looking at some that have 2 or 3 or 1, and we'll talk about that more on Wednesday. So peaks broadened by what we're going to call vibronics. And that is that they have varied vibrational and rotational energies. Energy levels, I should say. To give broad peaks. Very quickly here, we've seen this equation several times now. It's the Beer-Lambert law, or Beer's law. You see all sorts of different names for it. Which equates the absorbance with the log of the intensity of the incident light divided by the intensity of light leaving the sample, which is measured as absorbance here, and then can be calculated as epsilon times the concentration times the length of the sample cell, where epsilon is our molar absorptivity. So you can use this data to calculate epsilon in a given sample. And a couple things just sort of to note: if we have a log of epsilon that's greater than 4, which would be epsilon greater than 10,000, we would call that a strong peak or absorption or intense absorption. And if we have log of epsilon less than 3, so we're looking at epsilon less than 1,000, then that's going to be considered a weak absorption. And you can calculate those. The one criteria, though, or one thing to keep in mind, is you can only calculate epsilon if you have a very pure sample. So only that compound is in there, or even only that one species of that compound is in there. Sometimes we have different proton transfer states and things like that. That complicates the absorption. So you only can do it if it's one single pure species in there. Otherwise, the epsilon doesn't mean a whole lot.